Welcome to this presentation from the Theosophical Society in America. The Theosophical Society encourages open-minded inquiry into religion, philosophy, and science. And today we are honored to have Dr. Dan Hooper, who will answer some questions about what we know regarding this mysterious universe. Dr. Dan Hooper is a senior scientist and the head of the Theoretical Astrophysics group at the Fermi National Accelerator Laboratory, Fermilab. He is also professor of astronomy and astrophysics at the University of Chicago. He received his PhD in physics from the University of Wisconsin-Madison, and later did postdoctoral research at the University of Oxford and the David Schramm Fellow at Fermilab. Dr. Hooper has authored more than 200 articles in peer-reviewed scientific journals, and he has given an even larger number of technical talks at scientific conferences and university seminars. He is the author of a number of books and has appeared on several television shows. His newest book is At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. And I am, of course, very excited to have this opportunity to ask some of these basic questions regarding our universe from this expert. Thank you for being with us, Dr. Hooper.
It's my pleasure. Thanks for inviting me.
Well, to begin with, I guess the first question I'd like to ask is, what do we mean by the universe?
So, as with a lot of words in cosmology, it really depends on the context and who's using them. Different people mean different things when they talk about the universe. The original idea, we called it the universe, as in the singular everything. And that would imply that everything that exists would be in the universe. That seems to be a reasonable definition of the word. But most cosmologists don't mean it that way. I'll tell you what I mean when I use the word universe. What I mean is a piece of space and time, I suppose, in which the different things in that piece of space and across that time have the potential to influence each other. So if there are two different places that have two different objects that could never possibly even hypothetically interact with each other, I would call those different places to be parts of different universes. So that's what I have in mind when I delineate different pieces of space or existence into different universes.
So from that, it sounds as if you are quite open to the idea of many universes.
So I am. I don't think we can say we have any proof or indisputable evidence that other universes exist. But I think there are a lot of suggestive arguments for why they likely do. And if I just take kind of a historical perspective about this, I could imagine some people living on an island, many thousands of years ago, and they might have speculated about whether there were other islands somewhere out there in the ocean, islands they couldn't see or reach, and eventually they would find out there would be. And, if you asked somebody in ancient Greece, a philosopher in ancient Greece, they would have told you that the Earth is unique and that there are these planets and things that orbit it, but the Earth is this very special place at the center of the universe. And of course, we'd eventually find out that all the other things, or many of the other objects we see in the sky, are planets very similar to the Earth, in orbits around the sun. And around that same time, we would learn for the first time that our sun isn't unique. Our sun is one of many, many stars. Those stars in the night sky are really just the same kinds of objects as our sun, but much, much farther away. And it wasn't until the 1920s that physicists and astronomers learned that the Milky Way was not unique. It's one of a trillion or so galaxies that make up our observable universe. So continuing this, I think we might one day look back upon the debates we're having now about, universes and multiverses, and think that this falls in continuity with these other trends, where we learn that the place we happen to inhabit isn't as special as we maybe once thought it was, but it's one of many such realms that exist in a much larger landscape of reality.
Now, if we're concerned with our universe, what we consider this, what we, as you say, the observable universe that we are interacting in, how old is our universe?
So we actually have a pretty detailed understanding of most of our universe's history. We can observe over different periods of time how galaxies and clusters of galaxies and things like this, stars and planets, have evolved. After all, when we look far back in space with our telescopes, we're actually looking far back in time, because it takes time for light to travel across space. Mm-hmm. And if we look back far enough, we find our universe was a very different place than it is today. In particular, we can observe the light that was released into our universe when it was young and hot, something we call the cosmic microwave background. This light was emitted into space about 13.8 billion years ago. And it fills all of space today. We're bathed in it right now. It's very cold light. We don't notice it, but with a sensitive enough telescope, you can measure it and learn a lot about our universe at very early times. Going back even further, we can observe the amounts of different kinds of nuclear elements we find in our universe, how much hydrogen and helium and things like this there are. And those were things that were formed in the first second or so after the Big Bang. So this is even closer to that initial point that we call the Big Bang. And because our theory predicts the ratios of these different kinds of abundances, these different kinds of elements, and they match our observations, we're pretty confident that we understand our universe's history as far back as that. Going back even further requires a little bit more speculation, but we can inform our understanding of the very early universe by the results of particle accelerators, machines like the Large Hadron Collider. And before that, there was the Fermilab Tevatron, which we were very proud of where I work. Machines like these, in a respect, allow us to study the laws of physics that dictate the universe at very, very high temperatures, like those found in our universe in its first trillionth of a second or so. And we think we have a pretty good idea of how that played out, and a pretty decent picture of our universe's history from the point that we say is about a trillionth of a second after the Big Bang up to the present 13.8 billion years later.
We think that the Big Bang was the beginning, but why was there a Big Bang?
So if you took the original version of the Big Bang Theory, the version that people talked about in the 60s and 70s, and you looked at the arguments made by people like Stephen Hawking and Roger Penrose and others, it really seemed that if you took these equations that Einstein gave us, the equations of general relativity, and just ran them backwards, eventually you'd reach a point where there was a space-time singularity, we call it, where space becomes infinitely small. The temperature of the stuff contained in that space becomes infinitely high. And at that singularity, time and space itself seem to come into existence. And what I mean by that is there really wasn't any time that preceded this moment or this state of space and time that we call the Big Bang. Asking what happened prior to the Big Bang is like asking where on a map is north of the North Pole. There's just nowhere that those words point to. That being said, some things have changed about the way that cosmologists think about the Big Bang in more recent decades. In particular, a lot of physicists and a lot of cosmologists think it's likely, and I'd agree with them, that it's likely that there was an event that happened in the very, very early universe, where the universe grew very, very rapidly for a very short period of time. We call this era cosmic inflation. And it turns out that once you start cosmic inflation, parts of the universe will continue to grow in this very rapid way, continue to inflate forever. And patches of space will stop inflating, creating things that we would call universes, very large pieces of space that can look like our world, for example, while other parts of this inflating space just continue to inflate, creating more and more of these pocket universes. So if that really does go on forever, maybe there's not a need for a beginning in the way that we originally envisioned the space-time singularity, or maybe there was prior to inflation. Both of those, I think, are logical possibilities. I would encourage anyone to, be fairly open-minded about what the first, trillionth of a second or so after the Big Bang may have been like. It may hold a lot of surprises that we simply just don't know about or even how to think about yet.
Human nature, I think, in all aspects, like religion or creation or anything, we like to think of, well, there is a beginning point. And of course, then there's a question, well, what was there before that beginning point? And I guess that's the same with the Big Bang, is what was there before the Big Bang?
And in order to even conceptualize a question like what was there before the Big Bang, you have to have a time that existed to point to have that question make sense. It's not clear that there was any such thing as time, infinitely far back. Time may have come into existence at some particular, for lack of a better word, time. I understand that's a poor use of the word, but we don't have a language to really talk about these things.
But the general consensus today amongst scientists is that our universe is an expanding universe. It's expanding, is that correct?
That's right. So we've measured the expansion history of our universe very accurately. Right now, cosmologists are arguing about 5% differences between their measurements of how fast the universe is expanding. We all agree it's expanding, whether it's expanding at 67 in a certain number of units or 71. That's a very hot debate right now. But those are the sorts of things we're debating. We're not debating whether it's expanding. It has been expanding over the course of its long 13.8 billion year history. And all indications are it will continue to expand into the future.
Now that obviously begs the question for a layman. It's like, well, what is it expanding into?
Yeah. No, everyone asks this question. Every single time I give a public lecture, I get it. So I've thought about ways to try to convey this. So first of all, it's a question that doesn't have a very good answer, because if there were something that space could be expanding into, we would call that something space. And that's not what I mean. When I say space is expanding, I mean all of space. And it's not that there's some stuff somewhere moving into some previously unoccupied space. Instead, the space itself, all of it, is getting bigger without moving into something else. So I have this kind of mental trick that I developed when I was a grad student to kind of picture this sort of thing. So let's say I want to know how big the room I'm sitting in right now is, my office. So I get a meter stick and I put it side by side, and I find out that my office is 4 meters from wall to wall. Okay. And then I wait a little while and I do it again. And this time it takes 5 meter sticks. Well, I've just learned one of two different things. Either my office is getting bigger at a rate of 1 meter per amount of time that I had between the measurements, or my meter stick is getting smaller. Okay. I can't tell these two things apart. Of course, I would really only be tricked by this if everything in my office is shrinking together in unison at the same rate. But a universe in which space is expanding will, to us, in all respects, look identical to a universe in which all of its contents are shrinking. And when I say all, I mean things like the speed of light and the size of atoms and all the sorts of physical constants that set the sizes of things. So this is not a particularly plausible picture. It would require a huge conspiracy of different features that cause them all to shrink at the same rate. So I don't think that's how you should really think about it. But if you're struggling to picture expanding space without it expanding into something, you can equally well visualize a universe in which space is static, but all this stuff is shrinking.
Well, that is a mind bender. I'll try that one. So, I mean, it seems as if it's still the beginning and what was there before the beginning and the expansion and what it's expanding into, it certainly has an aspect of mystery about it. But obviously mathematically, and that's what is indicated.
Well, mathematically and also just observationally. We point our telescopes to the cosmos, and we can see that the universe is getting bigger. Things are all moving apart from each other in a way that they would if space were just uniformly expanding. We have numerous observations to support this on all sorts of different kinds of scales, using all sorts of different kinds of techniques and studying different kinds of objects. I think it's beyond debate at this point that the universe is in fact growing with time.
That being given, is this growing just going to continue with no end, or is the possibility of it coming to a point where something different happens?
The real answer is we don't know for certain. If we take what we know about our universe today, we see that the expansion rate's been growing with time. It hasn't been slowing down as we may have predicted some decades ago. We now know it's expanding at an accelerating rate. What it would take to cause a universe to expand in this accelerating way would be an energy associated with the vacuum of space. What I mean by this, and we call this stuff dark energy, by the way. So what that means is that if you take any cubic meter of space and you take all the particles out of it, all the light, all the neutrinos, all the atoms, everything, you would still have a certain amount of intrinsic energy built into that cubic meter of space. And it would be the same amount of energy at all times and all places. And that means that as the universe gets bigger and everything else gets diluted by the expansion of space, this dark energy, this vacuum energy becomes more and more important, causing the universe to grow faster and faster. And as long as that dark energy stays in place, and like I said, we have every reason to think it will, at least for a very long time, the universe will continue to grow at this exponential accelerating rate, just pulling everything apart from each other faster and faster. That being said, maybe a trillion years from now or something, that dark energy will decay away, turning into other sorts of stuff, causing our universe's future trajectory to change. We just don't know. We don't know enough about the nature of dark energy, why it's there in the abundance it is, or what its future or far future might be. But for the near term, I think it's clear the universe will continue to expand at this accelerating rate.
Now, you bring up this notion of dark energy. It's such a strange concept, dark energy. Is that just a misnomer, or, I mean, is it energy, or
yeah,
what can you say?
It is. So the adjective dark really just means it's energy we don't actually see. We see the effects of it, but it's not like light or something that we can get an image of. But what we mean by dark energy is the energy that's built into space, the energy that's causing the universe to expand in this accelerating way, this kind of energy density that doesn't dilute as space gets bigger. It's been part of the story of cosmology all the way back to Einstein, but we had real evidence for it in the 1990s. When we began to measure the accelerating expansion of space. And since then, we've measured its presence in many different ways. A nearly uniform consensus has formed among cosmologists that it's real. In fact, it makes up about 70% of the energy density of our universe today. So it's an enormous component of our universe. It plays the leading role right now in how it evolves and changes.
But its presence is deduced from what effects we assume is due to this presence.
In the context of general relativity, the only way we can explain the observations we see about the expansion of our universe is that there is this non-diluting component of the energy density. We call that stuff dark energy, but we don't know what it is. I mean, we measure its effects, we parameterize it, we learn things about it, but deep down, we don't really know what it is or why it's there.
Now, this is fascinating that we have great confidence, or the scientific community has great confidence in the existence of this, and possibly something like dark matter is similar. But yet there's just doesn't seem to be a way for us to actually directly see it or know anything about it other than its effects.
Well, I think that's true about a lot of things. I mean, we had a pretty good idea that air was there long before we knew it was mostly made of nitrogen and oxygen and other sorts of characteristics of it. We could tell that it was there because when we swing our hand through it, we can kind of feel this air resistance. We can feel breezes. We can, so we notice the effects of air, but we didn't know what it was. We just called it air, and it was kind of a placeholder, holding, stepping in for our ignorance. Maybe dark energy is something like that. We see its effects in many different ways. We have very little doubt that it's actually present and that it's responsible for these things that we attribute it to. But deep down, we don't know what the stuff is made of or why it's there.
Very good. I hope that the coming decades will reveal greater amount of information for all of us. But just one side issue on a point we raised at the very beginning with the possibility of there being numerous parallel universes that, obviously we cannot know because we cannot communicate in any way. But if that is a possibility, then would you say that they would be similar or have completely different characteristics and laws of physics or existence would be so radically different?
So you could imagine a variety of answers to that question. And it depends what kind of universe you're talking about. So let me walk you through several of the different motivations we have to posit these extra universes and kind of show that like some of these you might expect to be very similar, some you might expect to be entirely different. So first of all, near the beginning of this talk, you asked me what we mean by a universe. And I said a region of space that things can potentially interact with each other. But the universe is expanding. Our universe is expanding. And that means that if you go far enough away, you'll reach a point where even at the speed of light, you can't communicate with some other point. And that's because the amount of space between those 2 points would be growing apart from each other faster than the speed of light. So if you and I are separated by that distance and I try to send you a signal at the fastest possible speed, which is the speed of light, that light will never reach you because you and I are moving apart from each other at something faster than the speed of light. So I would say those 2 points are in different universes. So in that sense, we have a boundary, a sphere that surrounds where we are now. And it's very long. It's tens of billions of light years. And that sphere contains what I would call our universe. Mm-hmm. Now, I don't think space ends at that boundary. I think it's very likely space extends. And in that sense, there are other universes, probably a very, very large number of those universes. And I would be shocked if the laws of physics were very, very different just by traveling 1 or 2 universes over. Probably they have the same forces we have. They have the same kind of particles we have. The constants of nature are the same values, things like this. Now, maybe if you go 1 trillion universes over, some gargantuan number, you'll start to see shifts in those numbers. That's possible. Maybe even you reach some sort of point where there's a boundary, and on the other side of that boundary, the laws get really different. Maybe there's a different force or different kinds of particles on the other side of that boundary. These things are all possible. Then there are other kinds of universes, like the kinds that are made as universes inflating shortly after the Big Bang. We mentioned that before too. Yeah. These pocket universes could have just totally different laws of physics. The laws of physics are set by the kind of the shape of what we call the potential, or sometimes called the landscape or string landscape in the context of string theory. And you could imagine that there are a bunch of different places that a universe could find itself living in that landscape. And some of those universes might contain things like electrons and protons and forces like we know, and others would contain entirely different forms of matter and energy with different kinds of forces, maybe different dimensionality of space. Maybe some would be 4 or 5 or 16 dimensional, and others would be 3-dimensional like ours, or something else. I think we can be very open-minded about that array of possibilities.
You did mention an interesting thing. Well, it's a fact. You said if our universe expands sufficiently far enough, and then two separate points in that universe are sufficiently far apart that it would exceed the speed of light. I think you said we wouldn't be able to communicate. I'm just, do you think there is any way or possibility of transference of information that is faster than light?
I think it's very unlikely. Just taking what we know about the laws of physics, the theory of relativity strictly prohibits faster than light travel, at least through space. A lot of theories we've had have worked pretty well for a while, and then they're replaced by something else. So we should be open-minded that one day we're going to have a theory that supersedes relativity. It will probably look a lot like relativity in certain regards, but it will be different. And maybe that theory, you might say, allows for faster than light travel. But if you did that, you'd run into some very substantial problems or challenges. In particular, if you can travel faster than the speed of light, if something can, then you can show, I think rigorously, that in other frames of reference, that thing is traveling backwards through time. And if something can travel backwards through time, then you could build a time machine that would allow you to kill your grandfather before he meets your grandmother. Then you're never born, so you never travel back in time. So your grandfather does meet your grandmother, and you are born, and you can immediately see the logical paradox that ensues. Everybody who's ever written a backwards time travel book or TV series or movie or something has to deal with these sorts of, logical paradoxes that are intrinsic to that sort of thing. So it really does seem profoundly problematic for laws of physics to allow for backwards time travel. So if I had to make bets about which facets of our current understanding of nature will hold in the long run, that's probably one that makes the top of the list.
Now, my knowledge is very sketchy on this, and I may be really stretching myself, but I have read very little about these entangled particles. And so a characteristic of two, say, entangled particles, if one characteristic of one particle is observed, that immediately fixes the characteristic in the other particle, regardless of their geographic or wherever they may be. And that transformation or transference of information is what interests me. And that seems to be instantaneous with no medium.
Yeah, so this idea goes back to a famous paper that Einstein wrote with Podolsky and Rosen in the 1930s, the EPR paper, as we call it, for Einstein, Podolsky, and Rosen. And he thought, at least my understanding is of what Einstein thought at the time, is that this was a really big problem for quantum theory, and something that might show us that quantum theory as it was currently conceptualized couldn't be right. That's not how people view it now. People think that, quantum mechanics is weird, but it's not necessarily wrong because of this so-called paradox. So what he pointed out is that you could maybe, like an example of something that has this sort of entanglement is maybe there's a radioactive atom and it decays and two particles come out, one in either direction, and maybe they're spinning. So one spinning clockwise, the other one has to spin counterclockwise in order to conserve angular momentum. That's just a fundamental law of nature. And if these were ordinary kind of intuitive particles, like before we knew about quantum mechanics, then one would go out clockwise and one would go out counterclockwise and it would be fine. But in quantum mechanics, it says things don't exist in pure states. They exist in what we call a quantum superposition. So the particle going out this way is kind of both clockwise and counterclockwise, and the opposite one is both counterclockwise and clockwise. And the universe exists in a superposition until you measure one, find out what it is, and that fixes what the other one has to be. So imagine you do this and the two particles fly off for very, very long distances. They're still in their superposition. And then you measure one, you find is clockwise, and suddenly you collapse the wave function of the other some very great distance away instantaneously. And that sounds like you're violating this prohibition of traveling against the speed of light. It turns out, however, that if you actually do the math and follow it carefully, the logic carefully, you can't actually make information travel through the universe faster than light because of quantum entanglement. It's kind of a technical point, but I like to think of it as when you do this measurement, you simply find out what state the universe is in. You don't find out anything about, you don't actually change anything about the universe on its far side. And I'm aided by the fact that I tend to think about quantum mechanics in terms of a many worlds interpretation, where the wave functions don't actually collapse. The whole universe retains a superposition even after you make the observations. And in that sort of way of thinking about quantum mechanics, you can see there's no paradox anymore.
And the reason I raise that question is it's just, I know that your field is astrophysics and physical universe. I just obviously from a spiritual perspective, always interested in the idea of what consciousness is and how consciousness arises, and this, like some mental phenomena such as ESP and the idea of some information being able to be accessed across great distances instantaneously is always an intriguing concept to me. That's why I brought that up.
Yeah, so I mean, I'm a materialist deep down. I think that every facet of our universe can be described in terms of physics, basically, and if there is some means by which ideas or information or whatever can traverse space and travel from one place to another, I'm pretty sure it's going to have to obey the speed limit of the speed of light for these sort of time travel reasons mentioned before.
So we won't go down that rabbit hole much more. Now, regarding our own universe, it obviously, it's for us, it seems to be, so big that it's almost potentially infinite, and it's growing. How do you feel about intelligent life existing, in other places in this universe, or other planets and other galaxies? How does the scientific community feel about that?
So, I mean, my view is that, there weren't any miracles involved in the formation of life on Earth. It's a biochemical process that requires some rather special conditions. But if it can happen here, it could happen somewhere else. So it's not a question of whether, the Earth is entirely unique and in the sense that life evolved here. The question is, how rare is life? Is it something that happened many times in the Milky Way? Is it something that will only happen in 1 out of 1,000 galaxies in the course of the universe's history? Is it something that will only happen out of 1 billion galaxies, 1 trillion galaxies? Those are the sorts of questions we're asking. And I think we've made some progress on at least narrowing down the range of answers in recent years, in particular by studying the planets that are around other stars in the Milky Way. 10 years ago, there were very, very few planets that we knew about, and now there are many thousands. And we can characterize them, and we have a pretty good idea of how many there are. In particular, it looks like there are, billions of planets around sun-like stars at a distance that could support liquid water in the Milky Way. That's a lot of planets that life could potentially emerge on. And I'm sure a lot of these are not habitable for a variety of reasons. Maybe they have the wrong chemistry, or maybe their geological history wasn't ideal or something. But if even a very small fraction of those life could emerge on, there could be life in a lot of places in the Milky Way. We know from our own geological record that once the kind of conditions for life to emerge set in on Earth, it happened pretty quickly here. There wasn't a very long gap between the end of what we call the Great Bombardment and the kind of the cooling of the crust and things, and the first simple life forms to emerge. So that's at least suggestive. It's not proof, but it's at least suggestive that once the conditions are right, life will probably emerge. Now, where a plausible bottleneck may have happened in our own planet's evolution is going from simple single-celled life to multi-celled life. That took many billions of years or several billions of years, which makes you think that maybe that's the really rare thing. So maybe we're going to find someday that there are, thousands and thousands of planets in the Milky Way with life on them, but they're overwhelmingly simple microbial life or something like that. That's a logical possibility. Or maybe that will be wrong, and more complex forms of life will be more common. I will say this: if there were hyper advanced civilizations in the Milky Way, it would be hard to understand why we haven't noticed them. So look at what we've done to our environment, to our planet, through our attempts to accomplish a variety of goals. So, we wanted to feed ourselves and house ourselves and entertain ourselves. And, we build buildings, we build dams, we send planes and ships around. And if you did a casual observation of the Earth, you would notice us. Now imagine a civilization that's not advanced enough to do all the things we do and to travel to other star systems and to use a variety of hyper advanced technology we can't currently conceive of. It would be very hard to imagine that being undetectable. So I think it's very unlikely that there's hyper advanced life in the Milky Way right now or any particularly nearby galaxy. But that being said, maybe a billion light years away or something, that's the sort of thing we could easily go undetected by our current telescopes and technology.
And of course, these life forms, whatever they may be, need not necessarily be carbon-based as they are on Earth, I would think.
Well, carbon has some pretty big advantages. I mean, if you want to build a complex machine of organic material, carbon, it can make 4 different polar bonds, so you can do a bunch of complicated organic chemistry with it. Even if you had never studied life and you were just looking at the properties of different atoms and said, well, which of these would provide the best foundation for complicated living organisms, you'd probably pick carbon. So I think carbon is a good place to put your money on. People have talked about silicon-based life and things like this too. And maybe that's possible or plausible. But as far as naturally occurring, through evolutionary processes, spontaneous emergence of life, carbon does seem pretty special, as does liquid water as a solvent. So, my guess, it's just a guess, but my informed speculation is that the most common way that life emerges in our universe is based on carbon, organic chemistry in the presence of liquid water.
So the limitation, from what I've heard you say so far, as to why we may, if there is intelligent life out there, but we haven't been able to have any contact or observation, us of them, whether they have of us, may be limited to, is it that they are just so far away from us and the electromagnetic speed of these that we're sending out is not very fast? I mean, it's the speed of light, I guess, but it's not been that long.
Yeah, so there are two things. I mean, if something's far away, then maybe the signals haven't gotten to us yet. And secondly, those signals would be fainter. Just like sound or anything else, the farther you are away from a signal, from the emission of a signal, the harder it is to detect. So you could imagine that a billion light years from now, there's a civilization that's spread out through an entire galaxy, and they've built Dyson spheres around all the stars, and everything is super advanced, and they're dramatically terraforming their corner of the cosmos. And maybe to us, it just kind of looks like a red galaxy. It just looks like a dot in our telescopes. We can't, we haven't figured out yet all that's going on. But by the end of the 21st century, maybe we have the sort of telescopes and we can get a nice picture of that and see what's going on and discover that sort of thing for the first time.
So these advances in both being able to reach new information, do you see it being through mainly observation through telescopes of various sorts, or this idea of space travel? Do you actually think that humanity will, in time that's not unrealistic, be able to travel beyond our own solar system?
So I don't see any reason we couldn't do that. I mean, really, if we just decided to spend the resources to do it now, we could, for example, start planning and deploying a mission to Mars, a manned mission to Mars. Like there's some technical challenges that have to be overcome, but if we decided as a nation or as a world that we want to do this, that this was worth the price tag, there's no reason that couldn't be successful. Traveling to another star is, of course, much more difficult. That would require technology we don't currently have, but I see no reason that 100 years from now that couldn't be in the cards. There doesn't seem to be any law of physics saying that couldn't be done. That being said, I'm not sure that's the thing we would choose to do. And what I mean is, if all we wanted to do was learn scientific facts, I doubt we would have ever sent human beings into space in the first place. We would have spent unmanned or missions without human beings. We would have been using robots and other sorts of tools and whatever. A big part of the reason we send people into space is because of the effect it has on people on Earth. It's incredibly inspiring. Mm-hmm. I'm very glad that in the 1960s, NASA decided it was important to put a man on, or several people on the moon. I mean, I wasn't alive in 1970 when Neil Armstrong and company landed. But I mean, as soon as I was young enough to understand what that meant, it was inspiring to me, and it was inspiring to billions of other of us Earthlings. And I hope it continues. And I hope that, in my lifetime, we see human beings on Mars and other sorts of places in the solar system. I think that sort of inspiration and the sort of effect it has on the human species is worth the money, in my opinion. But when it comes to coming to other star systems, let's say this is 100 years from now or something, we're going to be able to build by then robotic or other artificial forms of life that can think very effectively, that can do a variety of tasks as well or maybe better than human beings. We're going to be able to build these things that in a way that they're not as subject to the harsh realities of space, cosmic radiation and other sorts of challenges, not to mention the challenges of just psychology, being pinned up in a tiny little vessel for years while you travel to Alpha Centauri or something. That's not something human beings are very good at doing. So it wouldn't surprise me if human beings never leave our solar system, but we will have an influence beyond the limits of our solar system through the things we create, our technological successors, if you will.
We will have to wait and see. I dare say, Dan, that although you may not have been around to see the landing on the moon for the first time with Neil Armstrong, I am confident that you're going to see the landing on the moon by probably a Chinese astronaut in not the too distant future.
That seems likely to me as well.
And do you think that going to Mars would be worth, the commitment, the expense, And what do you think we will achieve other than inspiration? And what discovery or what do you think scientific revelations would occur from such a venture?
Well, there's an enormous amount we can learn by studying Mars and other planets. And I'm sure by putting human beings on the surface, there are things we could do that couldn't be done by a lander or a probe or something like this. So there is science to be done. And of course, the question I'm most excited about regarding Mars, and other people might have other questions that they think are exciting. But for me, the exciting thing is, was there ever life on Mars? Were there ever the conditions on Mars that could support the evolution of life? And then, of course, looking forward, like, is Mars the sort of place that could support life in the future if we were to decide to relocate human beings there or some other organisms? That's what makes Mars exciting to me. I'm sure other scientists have all sorts of ideas about Mars that they think are exciting, but the one that gets me fascinated and excited is the possibility of life, past, present, or future on Mars.
I was intrigued to see that you had given a number of lectures or recorded a number of lectures on what Einstein got wrong. And I was, very interested in some of the concepts there or some of the aspects of science. Could you just speak on a couple of things that people may be surprised?
Yeah, so first of all, I just want to make clear that I hold Einstein in incredible regard, like probably like a superhuman level of regard. But I decided to do those lectures because, I don't think anybody does great things without making mistakes along the way. And deifying somebody to an imagined state of perfection, I don't think, is an accurate reflection of how human beings really are. So I tried to, while respecting Einstein and all his incredible accomplishments, spend a little time talking about some of the mistakes he made. And there were lots of them. It wasn't hard to, I think it was a 12 lecture series, and I filled them all with Einstein's blunders. We mentioned dark energy before. Well, he was the one who put that into his equations back in 1917, I think. And he put it in not to make the universe expand at an accelerating rate like we do now, but he put in the same sort of term in the equations to try to prevent the universe from expanding or contracting. He thought the universe had to be static. He really insisted on that. And he added this thing to these equations, which kind of was just like a fudge factor to make that work out. Of course, that turned out to be wrong. Our universe is expanding. And frankly, he should have been able to know that from the math before it was measured. He missed that huge opportunity to predict one of the most exciting or important observations or discoveries about our universe before it was observed. But okay, I'll forgive him for that. I think he got some things wrong when it came to gravitational waves. He wrote this very strongly worded paper arguing that gravitational waves couldn't exist. He was wrong about that. And very recently, we've started to measure gravitational waves from the mergers of black holes and neutron stars. So, long before we measured those, we were pretty sure that paper was wrong. But, he came down on the wrong side of that debate. That's another example. He seemed to have some issues with quantum mechanics that I don't think hold up very well to history. He played an incredibly important role in developing the theory of quantum mechanics, but he thought some of the weird facets of it were deeply problematic. And it turns out they're just weird, not necessarily problematic. So those are a few of the examples of things that we talk about in those lectures. But that being said, his accomplishments outweigh his blunders by a huge factor.
Yes, indeed. But I do encourage our audience or people listening to this, if you are interested, those 12 lectures recordings of them are available, and they are very, very good.
Well, while we're on that note, can I pitch something? So if your viewers might be interested, I'm co-hosting a physics podcast these days called Why This Universe with my co-host Shalma Wegsman. You can find that on any platform that you normally listen to podcasts. I'm pretty happy with it. We have about 20 episodes out and everything from black holes to extraterrestrial life to particle physics and cosmology, all sorts of interesting topics, and a little bit of philosophy of science thrown in there too. So I hope people enjoy that.
Oh, excellent. And now that you've brought up the topic of black holes, I don't think I meant to ask you about those because they're part of your expertise. Would you like to say
a lot of work on them lately? Yeah.
Would you like to say a little about those for us? Because it's like a mysterious thing.
Yeah, I mean, so it's another example of something that Einstein's theory predicts, but most people didn't think that they were real for a very long time after his theory was constructed. It wasn't until the 1960s that the theorists became pretty convinced that these things should be real. In particular, Roger Penrose made a very compelling case for how black holes should form at the end of the evolution of very massive stars. And then in the 1970s, we started to observe some black holes for the first time. We now know the black holes are pretty common. The biggest stars, when they complete their life cycles, become black holes. We also know that the cores of galaxies, probably all galaxies, or at least most galaxies, contain very massive black holes. Our own Milky Way has a black hole in the center that's several million times as massive as the sun. So really an enormous black hole. Like I said before, we're observing gravitational waves from black hole mergers. So these are two black holes in a tight orbit that are spiraling into each other. And when they finally merge, they send ripples through space-time called gravitational waves. And we've observed those from a dozen or so instances now. And then on a more speculative side, something I've been working on is it's possible, now we don't know this, but it was possible that black holes may have been formed, very small black holes may have been formed in the early universe. The first, fraction of a second after the Big Bang. We would call these things primordial black holes, and they could have had a variety of interesting impacts or influences on our universe, depending on how heavy they are and how long-lived they are. So there's a lot of cool stuff about black holes. They violate everything your intuition says should be true about the universe, about space and time and matter and energy, information, all these sorts of things. They're fascinating. In fact, since I brought the podcast before, the most recent episode is part 1 on black holes, and in about another week we'll put out part 2. So if you would like to check out Why This Universe on black holes, if you want to learn more.
But again, it's black hole in the sense that we have no direct way of getting information in or out of that. So it's by the effects of these things that we deduce their existence.
Yeah, so a black hole is surrounded by something called an event horizon, and this is a causal barrier. We can't know about anything inside of that event horizon, and if you were inside that event horizon, you can't know about anything outside of it. They're totally separate. In some sense, the inside of a black hole is a different universe from the one we live in some sense. Yeah. And we observe a lot of things about black holes, but they don't tell us anything about what's inside of that event horizon. They tell us about what's outside of the event horizon or immediately outside the event horizon. But that's all we'll ever be able to do.
And the laws of physics as we know them may not apply at all within that black hole. Would that be correct?
Yeah, I mean, if we trust the equations all the way down to the center, you reach a point where the density becomes infinite, and there's no reason to think the laws of physics that we have at our disposal apply to such a state. We would at a minimum, we would need some sort of theory of quantum gravity to talk about that sort of situation, and we do not have a theory of quantum gravity that we think we can employ in a trustworthy way at this time. That's a big goal of the physics community, maybe the biggest.
Is that still the hope of unifying the 4 fundamental forces, and that's the one that is hanging out there waiting?
Yeah, that's right. So a theory of quantum, well, right now, so we have what we call the quantum side of our understanding of the universe, which includes the electromagnetic force and the strong and weak nuclear forces, all kinds of elementary particles we know about. All that stuff is described by quantum mechanics, or in its more modern form, quantum field theory. And then on the other side, we have general relativity, which is a theory of space and time. And both of those theories are great. But we know that under extreme circumstances, very, very high temperatures or densities or something like this, the two theories do not play together well. They lead to explosions of infinity and nonsense, and something has to replace one or both of those theories and allow them to work together in some sort of coherent way. We call that theory a theory of quantum gravity, but we don't know what it is. And people talk about string theory and loop quantum gravity and other sorts of ideas, but these are they're brilliant ideas, and they've been explored by very talented scientists, but we don't have any way of knowing if they're really true in the sense that that's really how our universe works or not.
Well, it's been delightful talking with you, Dan, and I really appreciate your patience and attempt at making these ideas and concepts comprehensible for somebody.
I've had a good time, John. Thanks for giving me this opportunity.
Can I ask just one last question? Do you feel like science fiction writings, science fiction books, do you think that they serve well, science, or do you think that they just are like fake news sort of information that's put out there that just brings more confusion to the public?
Oh, the former. I don't worry about science fiction misleading people. I mean, it is word fiction in its name. Even if it's not true, it's fine. Like, I mean, it's imagination. I like reading Tolkien, and it doesn't make me think that orcs are real. It's okay. But that being said, I also think it's great for inspiring people to study science, especially young people who might get introduced to things like the idea of relativity or quantum mechanics or things like this. A lot of people learn about these things for the first time, or exposed to these things for the first time through science fiction. So it plays a very, very positive role in our society and culture.